Fine. So in yesterday's class, we were discussing about electromagnetic force or induction caused due to moving coil and a steady magnetic field, and static coil and a varying magnetic field. So we discussed about transformer EMF and generator EMF. So it's just a recollection of what we have done in the last class. So what do you mean by transformer EMF? The EMF induced in a stationary circuit. So circuit or loop is stationary, that means it is fixed, and magnetic field is varying across the circuit with respect to time. So B is varying with respect to time. How about generator EMF? And we have obtained the equation for this transformer EMF minus surface integral dou B by dou T ds. So here in the equation also you could see like magnetic field is varying with respect to time, and this is the equation for induced EMF, which can also be equated to closed line integral E dl. And also we come across another type of EMF, that is generator EMF. So what is generator EMF, guys? Can anybody tell me what is the generator EMF? So opposite to this. It is defined as the EMF induced due to the motion of a conductor. So here's the circuit or path, closed path is moving. But B is static. B is steady or in steady magnetic field. And we have obtained the equation here. V cross B dl. This can be equated to E dl. And finally, what if the situation, if we consider both the path as well as both circuit or path plus magnetic field, both are moving. So if both are moving, then the EMF induced will be equal to, suppose if I call this as equation 1 and this as equation 2, EMF will be equal to equation 1 plus equation 2. So this equation plus this equation. So there will be an EMF induced due to both transformer and generator EMF principles. Is it clear? So this is a very important question from the exam point of view. So make sure you know this concept very clearly. So next, we shall go to the concept of displacement current. Let me just try to remove this. So before I start displacement current, as per your syllabus, I just want to give you some kind of basic introduction on displacement current. And we are talking about time varying electric fields and magnetic fields, right? Here in this module. Let us just imagine a capacitor circuit. So this is connected to an AC source. Then the electric current is imagined to be in this direction. So in the positive half cycle of the capacitor will charge, and in the negative half cycle it will discharge. So this principle you know. Right. So now if you think about the magnetic field, whenever a current is flowing in the circuit, so the magnetic field is generated around the conductor. So what I'll do, I'll just place magnetic needles here. So these are magnetic needles which are sensitive to magnetic field. And one more needle between the plates of the capacitor. Okay, so these are magnetic needles. I'm just trying to give you an intro of what is displacement current. If you carefully observe, this has already been discussed in the class sometime, long time ago. So now I place this magnetic needle, and you could see when a current is passed, when there is an source, an AC source, when the current is passed, you could see the deflection of this magnetic field. The magnetic field will get deflected. Let us not worry about much about the direction now. Let us say the magnetic field is displaced or deflected with some angle theta here. Yeah, this is fine. This is acceptable. Why? Because I could see the magnetic field here. So this was the magnetic field, so which caused the displacement of magnetic needle. So what will happen here? My question is, what will happen to this magnetic needle when you have ignited or when you have allowed this AC current to pass through this conductor? What happens to this capacitor? What happens to this capacitor and the region in this capacitor? So it was surprised to see that this magnetic needle inside got deflected due to what? Can I call it as due to a magnetic field? If I say due to magnetic field, then my answer would be wrong. So then due to what? So this led to the concept called displacement current. See, let us just go back to the basics. You have a particle, you have a mass or a matter which consists of an atom, and if you have a conductor which consists of a particle of atom with in terms of electron, protons, neutrons and all. So if you have a charges, and if the charges are at motion, then you can say there is a current. And if there is a current, then you can say there is a magnetic field. Okay, you can say there is a magnetic field. So when charges are at motion, it introduces current. When current is flowing through a conductor, called as a magnetic field. So therefore, we applied an Ampere circuital law to measure a magnetic field at any given point, and that would be equal to the total current enclosed inside the closed loop. So this was our Ampere circuital law, and it holds good here. So here I is equal to what? I is equal to H dl is equal to I. So that is a total current, right? HDL is equal to total current. So this equation is applicable here, and I call this as conduction current, IC. So this equation holds good here also. Why? Because you have a current carrying conductor and there is a magnetic field which was generated, which made this magnetic needle to get deflected. But when it comes to this part, this equation fails. That means Ampere's circuital law fails to explain the concept of this deflection of magnetic needle. Why? Because there doesn't exist a charge particle. Charge particle is not there. Conductor is not there. It's an empty space. It's a free space. So if there are no charges, so what you will get with respect to current, because there is no movement of charges. So if there is no movement of charges, there is no current. So if there is no current, obviously there will be no magnetic field. Give me a second. I that Martin. Right. Yeah. Bye. Okay. So hope you got my concept. Hope you got this concept, like Ampere circuital law fails. I hope you understood this.
Yes, sir.
Okay, at least just let me know on the chat box if you have any doubt, or you may interrupt me if you did not understand. So now this theory completely fails. Why? Because we don't have a conductor here, a solid conductor, which will have charges and current and then magnetic field, which is making this magnetic needle to get displaced. So what is that happening here between these two charged capacitor parallel plates? So this magnetic field is getting displaced, or this magnetic needle is getting displaced due to the displacement current, or due to the rate of change of electric field. I repeat, due to the rate of change of electric field. That means electric field is varying. See, this is a very interesting concept here between the charged capacitor, wherein you are trying to introduce the new concept called varying electric field. Okay, so which will give you the displacement current, and I call this portion of current as ID. So what is this? Between the capacitor, this ID is nothing but displacement of electric field. So now I need to further modify this ACL, that is Ampere circuital law, needs to be modified. I cannot use the Ampere circuital law which was created or which was derived for static fields. See, the Ampere circuital law was derived for static fields. Now it is varying fields. It is time varying field. So I need to modify my Ampere circuital law. So as per the modified Ampere circuital law, if you look at this equation, if you look at this circuit, so the total current I will be equal to the conduction current which is going through the wire or a conductor, plus the displacement current which is happening inside the capacitor. So this is nothing but a modified Ampere circuital law. So here I could replace this by, so what is Ampere circuital law? I is equal to line integral H dl. So this is conduction current plus JD. What is this JD term? This JD term is nothing but displacement current density. It is the amount of current flowing on the surface of a given area. So I'll introduce this new term, and this is the modified Ampere circuital law. Hope you understood this concept. So now we shall take up the actual syllabus content. Now let me just try to format the background because it doesn't look good. I'll clear this canvas. Okay. Let us just go back to our syllabus. So now you might get a question in two different ways. One is either they will ask you explain the concept of displacement current. Explain the concept of displacement current with suitable displacement current with suitable equations. This is one way of asking the question. The same question, same concept can be asked as prove or obtain. So it is given in the notes. I am just going as per the notes. Prove or obtain Ampere circuital law. Modified Ampere circuital law. Sorry. Prove or obtain modified Ampere circuital law in point form and integral form, both. You might get a question in either ways. Explain the concept of displacement current or prove or obtain modified Ampere circuital law. So what is the point form of Ampere circuital law applied in steady magnetic field? So what is the point form? You remember curl of H is equal to curl of H is equal to G. I'll call this as equation 1. So this is the point form of Ampere circuital law obtained in steady magnetic field. So as this current density is due to the movement of actual charges, I already mentioned, see that this J is generated due to the movement of charge quantities which are at motion. Suppose if I take a divergence, now if I take a divergence of equation 1, what is divergence of curl? Guys, what is divergence of curl? Divergence of curl. Will you have a divergence for curl? See what is curl? Curl is a circular motion of a field. See, this is curl. Will you have divergence of curl? I'm asking you. So what is divergence? Divergence from a point, if you have an arrow, something which is leaving out from the point. Here there is no question of leaving out of this arrow from any given point. So it is rotating. So divergence of this curl will be equal to what? 0. So there is no divergence of this curl. So delta J is equal to what? 0. So call this as equation 2. But what is delta J is equal to based on continuity of current equation? So the current density is equal to minus, why this is minus? Minus rate of change of volume charge density with respect to time. So if you want to have a current on the surface of the volume, then it should be due to the decrease in rate of change of charges. See, I am repeating, it should be decrease in rate of change of charges inside the volume. It is as simple analogy as, suppose if you have a water filled balloon. As I already told you, this is a water filled balloon. In the previous example, I have explained this concept. So what happens if we want to have a current of water here on the surface? If we puncture this balloon here, so there will be a flow of water on the surface. See, there will be a flow of water on the surface here. So if I call this as a current of water, so what is happening? The current of water is due to the decrease of water inside the balloon. So here it is rho v. Rho v, this is dt. So d rho v by dt. That means there is a negative. There is a negative quantity because it is getting decreased here inside the balloon. The water is flowing outside the punctured area. So this is current here. So in a very similar way, so what happens with respect to the current density here? It is due to the rate of change of decrease in the volume charges with respect to time. So if I try to equate these two equations, see here, if I call this as equation 3, now this becomes a contradictory here. So you say delta J is equal to 0, but here it is giving me minus d rho v by dt. So when this equation 2 is 2, when minus d rho v by dt is equal to 0. But you cannot say d rho v is 0, right? So this is not applicable for time varying fields. So this cannot be applicable for time varying fields. So this is why I proved that there is a necessity of the modification for existing Ampere circuital law. But what happens with respect to the time varying distributions? D rho v by dt is not equal to 0. Correct? D rho v by dt is not equal to 0. Since it is a time varying fields. So this is a very important thing that what you need to remember or what you need to say before you want to change the Ampere circuital law, before you want to modify the Ampere circuital law. So everything everything is coming with respect to the example what I have what I quoted or what I tried to explain during the initial time of this class. So now, so this was one of the greatest motivation to introduce the displacement current term and also to modify Ampere circuital law. So what is modified Ampere circuital law? So followed by this, I'm just trying to move this slide away so to have a clean board. So now this happens to be to modify Ampere's law. So now I'll try to modify the Ampere circuital law by introducing displacement current, as I already mentioned. You're supposed to write these things in exam. Why you want to modify the Ampere circuital law? Because d rho v by dt is not equal to 0 in time varying fields. So this you need to quote, and then I'll introduce modified Ampere circuital law. Therefore, equation 1, where we had del cross H was equal to J. Now I introduce the term called J plus JD. Now I call this as equation 5. Now taking divergence on both the sides. Now I will take divergence because the divergence concept has led me to this conclusion, right? So now I will take divergence on both the sides. Del cross H is equal to J plus JD. Sorry, this is again del dot J plus, come on, del dot JD. So now what happens? Del cross H is equal to 0. 0 is equal to del dot J plus del dot JD. Sorry, del dot JD. Therefore, del dot JD is equal to minus del dot J. But what is del dot J? But del dot J is equal to minus d rho v by dt. This is due to continuity of current. There is a divergence of current due to the decrease in rate of change of volume charges with respect to time inside the balloon. Okay. So continuity of current. So now I could write this equation del dot JD is equal to dou rho v by dou t. I'll call this as equation number 6. Okay. But what is rho v here? So if you carefully observe rho v, the Maxwell's first equation, del dot D is equal to divergence of flux density is equal to rho v. See, as I've already told you, in capacitor, what is happening? See what was happening here? What kind of displacement current due to what cause? What was the cause of displacement current here? Guys? Due to varying electric field, right? Due to varying electric field, there was a displacement of current from this position to this position. And again, the current was a conduction current here at this point. Here till here it was a conduction current IC. So is IC is same across the circuit? IC is same, right? When you measure current here at this point, it should be same at this point too. Yes or no? No. Am I audible?
Yes, sir.
I asked you a question. Is current same here inside the loop?
Yes, sir.
So this IC and this IC are same. There is no alteration been done to this conduction current even after the charge capacitor played. And I call this as displacement current ID. And this ID is due to displacement of electric field. Can I say IC is equal to ID then? Guys, am I audible?
Yes, sir.
Can I say IC is equal to ID?
Yes, sir.
Okay, so the conduction current is equal to what? Displacement current. And already I have told you, I'm trying to get this term in your modified ampere circuital law. So what is this del? I'll replace this rho v by del dot d. This is Maxwell's first equation. So what happened to this equation? Del dot JD is equal to del dot dou d by dou t. So now compare the coefficients of divergence you will get JD is equal to dou D by dou T. Dou D by dou T is almost similar to dou E by dou T with some epsilon term. That epsilon depends upon the medium, dielectric medium, which is used between the charged capacitor or charged capacitor plates. So now I introduce this term. What is this current density now? Current density is nothing but the rate of change of displacement in electric field. So what is D here? This is epsilon E or electric field density. So what is JD now? JD is equal to dou D by dou T. So now if I substitute this to equation 5, so it is my modified Ampere circuital law equation. Substitute this equation to equation 5 here. So curl of H, therefore equation 5 becomes del cross H is equal to J, this current density, plus dou D by dou T. Call this as equation number, where are 6, 7? Okay, I'll call this as equation 6, and I'll call this as equation number 7. So this will be the final equation, equation number 8, where curl of H is equal to J plus dou D by dou T. What is J is equal to? J is a conduction current. J is conduction current. What is JD? JD is equal to dou D by dou T. This is time varying electric flux density. This is time varying electric flux density, also called as displacement current. Also called as displacement current, denoted by JD. Okay, so now this is a point form. So whatever we have obtained here, this is a point form or a differential form of a modified Ampere circuital law. Modified Ampere circuital law. Now, considering equation 8, we shall try to obtain the integral form. So in order to obtain the integral form, let us start with the equation 8. What is equation 8? Del cross H is equal to J plus dou D by dou T. Dou D by dou T. Take surface integrals on both the sides. You took divergence, right? So you took divergence earlier on both the sides, and you obtained what? Point form. So what divergence is a differential value, right? Dou by dou x, dou by dou y, dou by dou t, dou by dou r. So divergence always leads to a differential form. Whereas an integral, so you need to take a surface integral to get an integral form. So I'll take surface integral here. So take surface integral. Because I have not yet completed this topic, I'm done with point form. Now I am trying to derive surface integral form of modified Ampere circuital law. So take surface integral on both the sides. So I'll get surface integral of curl of H is equal to surface integral of J ds plus surface integral of dou d by dou t into ds. Okay. Now, if I apply Stokes theorem here, what is curl of any given vector? Yes, I forgot. So, what is curl of any given vector if I apply Stokes theorem? Surface integral of curl of any given vector is equal to the line integral of that vector. It's a vector line integral is equal to curl of that vector in surface integral. So I'll left hand side of the above equation, I'll replace it by L H dl is equal to surface integral JDS plus surface integral dou d by dou s into ds. Sorry, dou d by dou t. Be careful with this. Dou d by dou t into ds. So now if you look at this equation very carefully, this is an integral form, obviously. So is this equal to the total current I, which is equal to, this is a conduction current I C, which is equal to surface integral JDS, and this is what I mentioned about ID. This is a displacement current. So here you could see the total current is equal to the conduction current plus the displacement current. Again can be equated to HDL. So where IC is equal to conduction current. So here IC, I call this as conduction current, and ID is equal to surface integral dou d by dou t ds. Is a displacement current. Again, this equation again is one of the Maxwell's 4 equations in integral form, and now it is also called as Ampere's circuital law in integral form. So this is again one of Maxwell's 4 equations. So now we have derived this is the second one. Okay, this is the second one. So the first one is already been derived. What is the first Maxwell's equation? Remember? What is the first Maxwell's equation? Del cross E is equal to minus dou B by dou T. So this was your first Maxwell's equation. We'll try to consolidate all those equations later. This is due to Lenz's law, Faraday's Lenz's law. Okay. Any doubt?
No, sir.
Okay, fine. So let me just stop the recording and again